This is sort of a lengthy problem, so hang on. Lesson 1, number 7, we're looking at this function, which is a position function, and it's t squared over t minus 1. And part A asks us to find the limit as t goes to infinity of p of t. And this is important because right away I can tell you this limit is going to be infinity, and you can probably see that too. But on the midterm you're going to have to justify why that's infinity. I think it would be good to see one example of the basic idea behind showing this is infinity. So we can write this as, if we had for p of t, this is t squared over t minus 1. And technically this is equal to, in the top it's infinity, in the bottom it's infinity, which is so far unclear. So it's inconclusive what this is. But if we take and multiply the top by 1 over t and the bottom by 1 over t, this looks like the limit as t goes to infinity of t over 1 minus 1 over t. And now when we take that limit, that's equal to infinity over 1 minus 0, which equals infinity. So maybe not so surprising, but this proves that this limits infinity versus you just being able to look at it and see. So on the test we want to see you, when I mean test on the midterm, we want to see you algebraically manipulating this so that it's clear that it's either going to a constant, going to infinity, or going to minus infinity. And another thing that might come up is a left or right hand limit. So say that we're looking at the limit as t goes to 1 from the right of this function, of t squared over t minus 1. These you can't really show work when you're doing, but, well, you don't have to show work. But if you look at it, when we plug in 1 from the left or the right, the top is always going to be 1, and the bottom is going to be 0. So that tells us that this has to be equal to either plus or, since it's a constant divided by 0 means that it's going to blow up. But to decide which it is, it's either positive or negative, what we need to do is look at the sign of this function for small numbers close to 1. So if you imagine plugging in some small number that's just a little bit bigger than 1, or not some small number, some number that's just a little bit bigger than 1, then this denominator is going to be a small positive number. So this is equal to 1 over a small positive number. And what that's going to be is infinity, because if this is positive, then the quotient is always going to be a positive number. So the answer is just positive infinity. And I'm going to skip part C. For that one, you just plug in to the original function. There's nothing to even do with that problem. I'm going to jump into taking the derivative of p. So this is going to cover parts D, E, and F. I'm going to find the derivative at a point A. So first thing to do is write the definition. I'm fixing some number A, and the derivative is going to be the limit as h goes to 0 of p of a plus h minus p of a over h. And we know what p is, so we can plug in the corresponding values. So we've got a plus h squared divided by a plus h minus 1 minus a squared over a minus 1 divided by h. Now what we need to do is, there's this h here that's causing us to divide by 0, which makes it so we can't compute this limit. To fix this, let's do some algebra upstairs, ultimately pull out an h and be able to cancel this term. Since we have two fractions that we're subtracting, combining denominators seems like we can multiply this by a plus h minus 1 over a plus h minus 1, and this guy by a minus 1, a minus 1, and this becomes the limit as h goes to 0 of a plus h squared times a minus 1 minus a squared times a plus h minus 1 divided by, sort of messy, but a plus h minus 1 times a minus 1. And since the h was here before, if we keep track of our fractions, it's going to end up in the denominator of this expression. So next thing to do would be to expand these terms. And a little tedious, but it's a good exercise with your algebra. So first thing I'll do is I'll square this and get a squared plus 2ah plus h squared times a minus 1. And if I distribute the a, I'm going to get an a cubed minus a squared h plus a squared. And we're going to keep the same denominator. A plus h minus 1, a minus 1, h. And remember, we're still trying to cancel this h. And it looks promising. This is going to be a little too big to fit right here. So what I'm going to just do is write this numerator on this whole line right here. If I expand to this, I get a cubed plus 2a squared h plus ah squared. So that was distributing to a to each one of these terms. And if I distribute the minus 1, I get minus a squared minus 2ah minus h squared. And I have these terms right here. Minus a squared minus a squared h plus a squared. And I want to simplify this as much as I can. I'm sorry, this is an a cubed right here. It's sort of hard to write a 3 with a chunky pen. So if I look at the a cubes, these are going to cancel. These a squareds are going to cancel. I have a squared h term minus an a squared h term, so that means I have a squared h, if I take care of these two terms, an ah squared term, that's going to be by itself, plus ah squared. I have this ah term, looks like that's also by itself, minus 2ah minus h squared. So what I just did there is I accounted for all these terms and I tried to combine what I could. So this was just the numerator. And if we go back to our limit, this is equal to the limit as h goes to 0 of, so we get to plug in this new numerator, a squared h plus ah squared minus 2ah minus h squared divided by a plus h minus 1 h. And now I think we have an h in every term up here, so we can pull it out. And if we go to, I think I need another page to do this. This is equal to pulling the h out, limit as h goes to 0 of h squared plus a, h minus 2a minus h over h times a plus h minus 1, a minus 1. Cancel the h's, and we're left with the limit as h goes to 0 of a squared plus ah minus 2a minus h over a plus h minus 1 times a minus 1. And finally, that the h is gone, we can actually just plug in 0 wherever we see h and evaluate the limit, and we're left with a squared over a minus 1 squared. And that's the derivative. Lastly, so this is p prime at a. For this problem is they want us to find where, in part G, where is p prime of a equal to 0. So this isn't so bad because we just take a squared minus 2a over a minus 1 squared and set it equal to 0. And if we cross multiply, this becomes a squared minus 2a. I can factor out an a and write this as a times a minus 2 equals 0. And since we know that a is greater than 1, it says that in the problem, that implies that a equals 2 is the solution that we want. So like I said, kind of a long problem, but it's really important to get practice with taking derivatives using the limit definition, because you'll need to show all of your work doing these problems on the exam. And the thing to always look for is canceling the h term, like we did at this line right here. That's the critical step of these problems, is getting rid of that h in the limit definition. Good luck.